Sorry, we have to stop here. Feel free to ask more questions during the panel discussion. And our next speaker is James Tompkins. He's currently an assistant professor at Brown University. He has done a lot of very interesting work in vision graphics and interaction. And if you look through the Google, like you find Rear Window Augmented, you will see a completely new view of the old movie. Let's give it to James.
Thanks. Right, thank you for the introduction, and thanks to Philip for doing all the hard work in setting this up. So I'm going to talk about two extensions of CycleGAN for unstructured image-to-image translation. So we know that neural style is pretty good at representing local texture, but many times translation involves more than just local texture. So here, for instance, we might want to translate between the domain of human faces to anime faces, and CycleGAN, for instance, would be able to translate the local texture, but not really make that shape adaptation. So I'll talk about that first. And then the other thing that these approaches tend to have trouble with is the confusion of the foreground and background. So many times in a translation task, you might not want to translate the background, and maybe only you want to translate the foreground too. So we'll talk about ways that you can not translate the background, but still translate the foreground. Okay, so let's talk about shape. So this is work that was done by two undergraduates, Aaron and Vivek. Vivek is around at CVPR, so if you see him, say hello. Let's see. So let's start with the goal. We want to be able to translate between two domains, and we want to be able to translate both the local texture appearance of objects, but then also some of the shape appearance as well. So if we try to apply classic techniques, then, for instance, our dog to cat doesn't really work. Right? There's too much variation between the two domains for some examples to have this work. So our goal is to translate both of these things at the same time, and to try and capture more of the variance that exists within the domain. So here's what we can do. So this is a test set example of a cat, and we're able to make it kind of look like a dog, and then the other way around. So the images are, still a little bit blurry, but we've managed to translate the shape of the face. It's now a dog head instead of a cat head, and some of the fur has changed as well, things like that. Okay, so let's go through a set of improvements that we can make to the classic CycleGAN formulation to be able to pull this off. Okay, so we start with exactly the same setup that Philip just described. We have a discriminator for the source and the target domains, S and T, and then we have a function, F, that maps from source domain to target domain, and then back again with the function G, and we enforce that the distance, once you have gone from S to T and back to S, is small. Okay? So this is what we start with. So now our problem is, how can we introduce more of this awareness of the global, let's call it global, shape of the object, rather than just the local texture appearance. Okay? So in this example here, we have managed to somehow translate some of the local texture of the dog to the cat, but it still looks like a snout rather than the little nose of the cat. And what we really want is something more like something from the road. Okay, so let's see how we can encourage the generator to be able to do this. So first we start off by specifying our cyclic loss as something that is both more perceptually relevant and a multi-scale. So there's this idea that comes from image compression literature, image restoration literature called multi-scale structure similarity. And let's just look at the structure similarity part first. This is a measure of appearance distance between two images, which is closer to human perception than L1 or L2. Okay, and how does it accomplish that? It has three terms. It has a luminance term, a contrast term, and then a structure term. Okay, and the luminance term tries to measure the difference between two patches' luminance, and it does that in a very simple way, just by looking at the means of those patches. This C here is just a constant for the divisor, so that we don't run into numerical precision errors. Okay, and so when ux and ui are very similar, this will come out to something close to 1, and when they're dissimilar, it will come out to something close to 0. Okay, but this doesn't really help us. The things that really help us in representing more of the structure are this structure term on the right. And here we're looking at the covariance of the patches in the image. Okay, then we apply this structure similarity measure, multi-scale. So we downsample the image and run it again, and downsample the image and run it again. And this gives us more like an area statistic type loss. Okay, and this helps us to represent some of that extra shape information. Okay, so that's the first thing. And we mix this with the L1 loss and the GAN loss that Philip was just talking about. Okay, second point. Philip made this great point that the receptive field in the discriminator is really important. Right? The more that you can show the discriminator, the sharper your images can be. Right? But this comes at a cost sometimes. Sometimes the larger the receptive field, the more expensive it can be. So we're going to take an idea from semantic segmentation, actually, and we're going to introduce dilated convolutions into the discriminator. So a dilated convolution is one that only sparsely samples the image. So every second pixel, for instance, in a dilated by 2 convolution would be skipped. And effectively, as your layers build up, this increases the receptive field size of each of your convolutions. Here we see the effective receptive field size in blue, green, pink, of a dilated convolution relative to regular convolution on the left-hand side. Okay, so we're going to introduce these into the discriminator, and this is going to give us more of that wider context. Okay, so our discriminator now looks like this on the right-hand side here. So we have some regular blocks, but then we introduce these dilated convolutional blocks. But to make sure that we still carry some of that local texture through the discriminator, we have a skip connection that passes that information along, and that's concatenated at the end where the discriminator then makes a decision. Okay. So the thing that helps to improve is that our generator is slightly different. So we add more res blocks, which help to increase the effectiveness of this mapping, and then we add skip connections again within the generator, and this helps to push some of the local texture through the generator, even though we're going quite far down. We have a narrow bottleneck in our generator. Okay, so there's those three things that we do. We use a slightly different loss, where we introduce this multi-scale structure similarity. We have dilated convolutions in the discriminator that expand the receptive field, but still give us a similar cost computationally. And then we add these skip connections and more res blocks to the generator. Okay, so let's see how it does. We're going to introduce a toy data set. Okay, I really like toy data sets for getting to whether a technique is actually doing something useful. So here's our toy data set. It's polygons and dots. Okay? The polygons are meant to represent the overall shape of objects, and the dots are meant to represent some kind of texture of the object. Okay? And we're going to transform these dots and these polygons, and we're going to see what the techniques can do. So we generate a random 3 to 7 sided polygon, and then a uniform dot grid. And we also generate a random transformation. It's a 2x2 matrix, and then a 1x2 translation. So this gives us all kinds of displacements, rotations, shears, and scales. And you'll notice that something different is happening between the dots and the polygons. Okay, so given a transformation H, the polygon undergoes H, but then the dot pattern actually undergoes the inverse of H. Right? If we had the same transform, for both of them, it will be very easy for the network to learn. What we want to be able to split apart is this separate representations and abilities to handle shapes and textures in the network. And that's a strong statement, but let's... Okay, so on the left here, we have the input regular domain, and we want to translate this into the distorted domain under this transformation H. And Discogan, which Philip mentioned, was one of the contemporaneous cyclic loss GANs, just tends to regress to the mean. But in this instance, it's still able to encode all of the information it needs to translate back to a regular domain. It still solves the problem. It's just that the translated domain isn't useful, right? CycleGAN does a bit of a better job, and we do okay in this instance. Let's look at the other way around. Now here's CycleGAN, the patch-based loss has managed to reproduce this dot pattern, right? But it's not the right dot pattern. Here we want the transformed dot pattern. Now I'm not quite sure that ours is doing exactly the right thing, but it's slightly more in line. The other thing to note is that CycleGAN does a pretty good job of estimating the shape of the polygon, right? But the true location of that polygon in the input domain is in the middle of the image. Okay. And here it hasn't been able to translate that back to the middle of the image, whereas our technique has. And this will come into play in one of the data sets we'll see later. All right, so let's look at it on some real images, now that we've tried it on this toy data set. So Aaron, the first author, he loves anime. Okay, so let's do some human to anime. And all of the techniques do kind of okay. We have slight improvements, but this was even a bit surprising to me, that we can reproduce the sort of the band, the blue band in the hair, or the wisps of hair while still maintaining, approximate eye structure. The jaw has receded to that classic anime shape. The eyes got big. Right, looks pretty good. Let's go the other way around. Let's go anime to human. Right, this is much harder because we're really good at detecting wonky-looking faces. It's getting better. Getting better. Okay, so this is the domain in which we transferred the shape and the style. Okay, but let's look at an interesting domain where we just translate the shape. So these are still photographs, but we translated the shape. These are humans to dolls. Okay, and again, the techniques do broadly okay. We're making minor improvements over the existing approaches, but that's good. And then, of course, the other way around, dolls to humans. Which is a bit weird, but also quite neat. Okay, let's look at a more complex data set. This is the one where I mentioned this idea of moving would be relevant. So this is now not just frontalized faces. This is cats to dogs, and the faces of the dog or the cat appears in various different positions within the image. Okay, and there are multiple poses, varying lighting. It's a slightly more difficult data set. And here we're able to face swap cats and dogs. Let's look at the effect of the discriminator types on this task. Okay. So on the easier human to doll task, we had the classic patch-based discriminator. We could have a dense discriminator like Discogan uses, or this dilated convolution discriminator. And it happens that these dilated convolutions really help in managing to capture some of that shape appearance. Okay? So how can we quantify this? Because all of these networks still feel like, they still think they're solving the problem, right? They have managed to map between the two domains. Okay? So let's try and use a classification network. Right? Let's see if a classification network can see whether it's a dog or a cat. Okay? So let's use ResNet 50, for instance. Okay, but it turns out ResNet 50 is fooled on these kinds of images. It thinks that all of these are dogs. Right? And so CycleGAN and Discogan are acting sort of adversarially here where they're able to still fool the classification network into thinking it's a dog, even though conceptually it doesn't look like a dog. Okay? We only managed to get this kind of thing to work when we used a classification network that already used dilated convolutions. So we used DeepLab v3. And this is a per pixel classification network. And red is a pixel that is assumed to be a cat, and blue is a pixel that's assumed to be a dog. And here we got some success. Okay? Alright. So you've all been thinking, if I can do humans and I can do cats, can I do humans to cats? And the answer is, yeah, sort of. Some of these are quite good. Some of these are, needing improvement. This one down here looks like a rug. But some of them are quite amusing. And then, of course, cats to humans, whether you wanted to know what your cat would look like as a human being. All right, one thing I really like to do in trying to see where your model breaks, right? It's really easy to see where your model breaks if you run it and try and run it in real time. Okay? So here we go. Here's Aaron pretending to be a cat. This was yesterday. Here we go. Right, and you'll see that as the crop size gets to be about what the training data was expecting, it starts to look like a cat. But that we don't have enough cats with mouths open in the data set to be able to get that quite right. Okay, here's me as well. And we can also see that things like occlusions don't work very well, so I'm going to hold up my glasses in a minute. And you'll see that it completely breaks the model. Right. So there's a few things here that we could do to improve. This was ECCB 2018, but this area is moving so fast. So I asked the authors what they would do if we had to build this today. Okay. So first off, we would we use a classic GAN loss. We replace this with a least squares GAN loss. We'd use an identity loss on the input, and this would remove some of that color cast flickering that you see in the video there. Okay. We don't actually have an explicit sort of multi-scale loss on the discriminator. It's only implicitly through these diagonal convolutions. And then if you want some style, you could start adding that. This is like the most photographed slide. All right, so we can improve this shape change ability with some simple architectural changes. They're not big or clever, but they do make a little bit of an improvement. We can add a dilated discriminator, we can use this multi-scale loss, and then we can use this skip connection in general. And the toy example here demonstrates the power of this equation. Okay, so that was shape. Let's do backgrounds. This is work from Yusuf Najati. He's a PhD student at Bath, and he's currently an intern at Adobe. Okay, so our problem now is that sometimes in some tasks we just want to translate the foreground. We don't want to translate the background. Okay? How can we do that? So it kind of makes sense that this is a difficult task for these kinds of approaches, right? The image is being represented as a combination of both the foreground and the background. Okay? And our discriminator is trained on trying to look at the whole image regions. Okay? But what we really want to be able to do is just focus on the foreground. What we'd like to be able to do is somehow learn in an unsupervised way how to estimate a kind of attention map. Right? It's like a segmentation that tells us where the objects of interest are within the data. Okay? So this is our goal. As before, we're going to start with the CycleGAN framework, but we're going to introduce a new image formation model. It's very simple. That's going to ask the GAN to split up the image into two components. Okay? We're going to ask it to split up every image into a foreground component and a background component that are modulated by a mask. Okay, this mask is SA, and we get the two components by the element-wise product of the mask by the translation from source to target of our image S, plus the untranslated background region modulated by this mask. So how are we going to do this? We need to generate this map SA, which is what you saw on the previous slide. So our framework is going to look something more like this. S comes in. We want it to be read by, or looked at, by a new network, which is an attention generating network, AS. Okay, and then only the foreground part is going to be converted into the T domain by F, and then we're going to have to run attention on that converted part, again by A now T, to produce back our signal plots. Okay, let's look at that in a bit more detail. So here's our input image, and this is going to be fed into our generator AS, which is going to spit out an attention map, and it's going to look something like this. This is SA. Okay, and then I'm going to element-wise product this with the foreground, with the original image, and that's going to produce me what I think is the foreground component. And then I'm going to pass this into the translation function, which is going to produce me some psychedelic horses. And to get rid of the craft, I'm going to then reapply the element-wise product. Okay, and in the background, I just want to keep that along. So I take the 1 minus the attention map, and then I'm going to add together the foreground and the back. Okay? All right. So, why does this work? Right? It seems kind of like magic, that you can just ask this to generate you foreground and background generators, and it will just do it. Okay? So let's see. If SA is all ones, then this is just cyclic. But if SA is all zeros, then my output is equal to my input, and I'm never, ever, ever going to fool my discriminator. Okay? So, AS must focus on the parts which the discriminator thinks are important to be able to fool DT. Right? And the parts which are most consistently distinctive across the domain happen to be the foreground. Right? Horses look more consistent across images than the backgrounds of the images the horses are going to do. Okay? That's it. So now we can generate results that are, somewhat plausible foreground masks. They're not perfect, but they're okay. And this helps us only translate the foreground in a completely unsupervised way. Okay, what do these attention maps look like? So they're okay. They're not perfect. These are the floating point versions of those. Okay, they're not too bad. If you pass in an image that does not contain, in this case, a horse, the attention map does the right thing, almost, and is mostly that. Okay? How about 3 minutes? 3 minutes. Okay. So, this is the kind of weird situation, right? We're really trying to make a fake image. It really has the foreground from one domain and the background from another. Right? So this shouldn't really work. Right? It's a bit of a chicken and egg problem, right? I still have to fool the discriminator, but how does the discriminator know what to look at in this fake image if I just wanted to look at the foreground if I haven't yet trained the attention networks? Right? So I have this chicken and egg problem where I wanted to just look at the foreground, but I haven't yet trained it to just look at the foreground. Okay? So it turns out that you can fix this with a reasonably simple 2-stage training process. So for the first 30 epochs of training, the discriminator gets to see the whole image, and we train the attention network. And then we freeze the attention network, and then the discriminator just gets to see the foreground for the rest of training. Okay, and this is sufficient. There's like a sweet spot for what the attention network learns. Let's have a look. So as the epochs progress, it learns more and more about what is most discriminative about the domain. But if we leave it for too long, it starts to representing things that are shared, like the sky and the grass. Sorry, the water, right, between the two domains. So we don't want that. So we cut it off at 30. It's not ideal, but it's okay. All right. This is a timely idea. There were at least 3 or 4 works that have an approximately similar idea. And here's some of them. So this is a useful thing now that's being integrated as sort of an intermediate operation in lots of generation networks. Okay, so to summarize, representing this foreground and background distribution separately can be helpful for us sometimes if our task is only to translate the foreground. And so we can learn in an unsupervised way this soft attention map that can help us disambiguate these two. And that this can improve the quality of the image overall by separating out the background component from the foreground component that the generator has to do. Okay, one more thing. I had a really good holiday last year. In my tandem cycle, so we went to the Netherlands, it's me and my partner, right? It was pretty great. We just kind of cycled around. It's the Netherlands, it's kind of beautiful. Just me and the bike. Just cycling around. Wait a minute. What's this? What is this? Oh yes. It's not horseplay, it's horse cosplay. Okay. What's it gonna do? We can do horse to zebra, not too bad. Can we do over to this? Predictions, please, from the audience. You are all confused. Okay, well, I was a bit surprised too. Here's zebra to horse. Here's horse to zebra. It turns out that the frequency of the zebra patterning on the cloak, I think it's a cloak, on the horse cloak, is not representative of the frequency of zebra patterning. It's too high frequency. And so the generator hasn't really learned, the attention map and the generator haven't really learned to translate those parts. But on the face there, it's done a better job. Here's another view. So it's tried on this face mask, but then the rest hasn't. Curious. Okay, but wait. There's another set of horses. More horse cosplay. What are these ones wearing? Oh yeah. Now this one, surprisingly, this is what I don't understand. Right? This one kind of works. There aren't anything in the domain that looks like pink flowery zebra, horses. But it does okay. So if anybody has any suggestions for why that works, let's talk about it in the public group. All right, thank you very much.
I would like to just make a quick announcement. Because we start late, we will start the second tour at 10:30. Now it's a coffee break.
Right.